This video is the second part of the conceptual overview of the flexibility method. If you haven't watched the first part, please watch that first because this video will go a little bit quicker. The note there at the bottom of this slide simply reminds us that this method is also known as the force method or the method of consistent deformations. Why that's the case was explained in the other video. Let's switch now to pencil and paper. What I'm showing here is the same problem that I looked at in the last example. It's a propped cantilever beam fixed at the left end, roller on the right, cross-sectional properties EI, the ends are labeled A and B, uniform load W, length L. The change is that here I'm looking at a different primary structure. We already calculated in the last video that this is indeterminate to the first degree. And in the last video we removed this roller right here. Here, we are removing the moment right at the end. One way of thinking about that is that I'm turning the fixed end into a pin. I'm indicating here that there must be a moment acting on the beam at this point to replace the fixed end that I removed. We'll call this M sub A. Here, I'm showing the deformed shape of the primary structure subjected to the applied load. This is the undeformed shape, uniform load is the applied load, and we have a smooth curve like this. The relevant deflection that we need to keep track of is the rotation over here at the end. The actual support should maintain a flat slope over here. On this deformed shape, the slope is decidedly not flat. We have an angle here, and this angle we're going to call theta applied. So that is the error that we've introduced by removing the fixed support to obtain the primary structure. Now I'm interested in applying this corrective force, or the redundant, to the primary structure. If the applied load made this rotate clockwise, the corrective force should make it rotate counterclockwise. So even though I've drawn this here in the positive direction and the positive direction for internal moments, I'll draw it here in the direction in which it physically acts. If I apply a moment in this direction, in this counterclockwise direction, I will rotate the beam to that orientation, and the rest of the deformed shape will look roughly like this. I'll impose here an angle which I'll call theta CORR, or the corrective angle. That's the angle that will be applied to correct this error that we introduced in the first place. How large this angle is depends on the scaling factor M sub A, this unknown moment at the end, so that this angle is equal to the original error that we introduced. Stated a little bit more mathematically, we have that the rotation for the applied load is equal to the rotation for the corrective moment. We're keeping the deformations consistent with the boundary conditions, in other words, flat slope. If I look at my tables, I have here a simply supported beam, uniform load. The rotation at either of the ends, F4 or F5, are equal in magnitude. WL cubed, our load is W, so WL cubed over 24 EI. This is equal to the value for a moment applied at the end of a simply supported beam. Here I have a simply supported beam, pin roller, a moment applied at the end, and I'm looking for the rotation at the end where I'm applying the moment. That's F1 right here. That's ML over 3EI. M I'm calling MA, L over 3EI. Once again, this is called the force method because the force is the primary unknown, so I can solve this for MA. The EI's will cancel, there'll be a WL squared here, and the factor here is 8. So I get WL squared over 8. At this point, we just need to solve the other quantities by statics, so I'll actually bring the work that we did on the previous problem simply to illustrate what we should do, but we won't spend much time on this. In the previous problem, we first started out by finding this force here, and eventually found, through statics, that the moment was WL squared over 8. So you can see that no matter which primary structure we start with, there's only one physically correct answer. In this particular case, we would start by knowing MA, and we would have to find RA, and this value here, RB. If you don't quite feel comfortable that you're able to go through the whole procedure to find the unknown forces given MA, give it a shot. These are the answers. You should find that reaction at A is 5WL over 8, the reaction at B is 3WL over 8. Do it, make sure you can go through the procedure. So this video is intended to do two things. One is to show you that there's no single primary structure that has to be used to solve a problem. There's a choice in primary structures. It turns out that some will be vastly simpler to calculate with than others, so it certainly is an important choice. The second purpose was to illustrate this particular primary structure, that is, instead of removing supports, inserting moment releases at the location of the support. We'll use this concept more extensively when we look at continuous beams, because it turns out that even though this type of primary structure is more confusing initially because you're dealing with these rotations and it's not quite as intuitive for a student, it actually simplifies a lot of the subsequent work in the flexibility method. So this has now been introduced, and we'll use it in a subsequent video.